Everyone, let's talk about the Wilkinson power divider. Now, as you can imagine, there are many situations in microwave engineering where I would like to split a signal in two, right? Say I have a synchronization signal that I want to feed to two separate devices and have them run off that same sort of clock maybe, or maybe I have some sort of antenna array and I want to feed the same signal to two different antennas, that sort of thing. There are just many situations where I need some sort of input signal to be branched off into two separate signals. So one very simple device for that is the good old T section, right? And we talked a little bit about this earlier. Now, a problem that we emphasized in this class is how the T section is not really ideal because it's mismatched, right? So you do a simple model here where I have a 50 ohm line feeding a branch to two other 50 ohm lines. And you get the problem where the equivalent input impedance looking down into this branch, I see 50 in parallel with 50, which is 25 ohms. So I get a mismatched line here. That is to say, I have a signal will come in, and yeah, it'll split equally into two parts, but I suffer from the trade-off in that I'm going to get a reflection back out of this port. And that'll be true no matter which port I'm looking into as well. So think about that in terms of just generic microwave theory, in that we had that trade-off between matched loads, reciprocal, or matched networks, reciprocal networks, and a lossless network. And when you add the option, you can pick any two of these, but you cannot have all three at once. So just looking at the T divider, you can see how it is going to be lossless, right? It won't actually absorb any energy in here. And it's going to be reciprocal in the sense that, it's going to kind of behave the same no matter which port I excite, but it was not going to be matched. So that was our sacrifice with the T junction. And it's tempting to try and cheat this a little bit. Like, for example, suppose instead of 50 ohms, I replace this with 100 ohms, like this. So I have a 50 ohm line feeding a split into two 100 ohm segments. And now you can see how the equivalent input impedance, seen looking down here, will in fact be a match at this port. And so maybe that's great, but you also notice that that's not entirely desirable because now I have to deal with a 100 ohm line instead of the usual 50 ohms. So either everything else down here has to be designed with 100 ohm impedance in mind, or I now have to insert some kind of impedance transformer to bring everything back down to 50 ohms in order to make this work. You also notice that if I excite it from a different direction, I'm basically getting worse reflections now as a result, right? So originally I had, just kind of a moderate amount of reflection at all these ports. So in exchange for getting some good match at one port, I have made the match even worse at the other ports. So it's a nice little device. It's cheap and it's simple, but there are many practical applications where this just isn't going to work out very well for me. So in exchange, and I guess to get around that, a very common device in microwave engineering is this here. It's called the Wilkinson power divider. And you can think of that as sort of rearranging this trade-off here. So what I am going to get is actually I'm going to get a match, and it's going to be reciprocal, but I'm going to sacrifice loss in exchange to get these properties. And I'm going to be okay with that because these properties don't necessarily have to apply to all ports. That is to say, I can have a match at one port, even if I don't have a match at my other ports. I can be lossless for a signal coming in this way, but I may not necessarily be lossless for a signal coming in some other direction. So even though it's not perfectly lossless, I do have the property where if I'm at least injecting it in this direction, I will get an equal split of power without any loss. Even though if I do the opposite, I may lose some energy, and that's okay. Okay, so what we will do is we will derive the S matrix that corresponds to this device. And the derivation's a little interesting. It's a little tricky too, so try and kind of follow along as best as you can. But the end result is actually pretty straightforward once you get to the finish line. Okay, so it's a little bit hectic, but the result is simple enough that you can do a lot of practical things with it once you find it. Okay, so you'll notice I've redrawn my Wilkinson power divider here. So just a quick overview. Originally, we had a characteristic impedance here at port 1 of Z0 coming in and would split into two. And ports 2 and 3 also had a characteristic impedance of Z0 coming out. In between, we have this sort of T-split where the impedance is chosen to be square root of 2 times Z naught. And we also have this resistor here with a value of 2 times Z naught. So you look now here, I've replaced a few things. In particular, you'll notice that Z is just a generic impedance. I don't necessarily know what its value is yet, but we're going to show that a value of square root of 2 times Z naught is in fact the ideal choice. Likewise, that resistor, you see I've broken it up into two series values, both of a value of R, a resistance R, and we will find that a value of R equals Z naught is also an ideal choice here, so that when they add together, I get 2 times Z naught for this resistor. And looking down here, you see I have a characteristic impedance of Z naught, but I've replaced it with two resistors here, each of a value having 2 times Z naught. So the idea is, from the perspective out here, it's still going to behave as if it's a matched load with a value of Z naught, because the parallel combination of these two resistors will be Z naught. Over here, I've also created the standard scattering matrix. Okay, so this is just the definition of what a scattering matrix represents. And you'll notice, since everything here is passive, I've made it symmetric here. Okay, so these diagonal terms are all equal to each other, but I don't necessarily know anything else about this matrix. But I'm going to impose certain conditions over here to create ideal results out over here. So finally, you notice I've created two voltage sources here, and these are going to represent voltages, incoming waves that will excite this network from the right. And that's going to tell us a lot about kind of the behavior of this network and allow us to fill it in this matrix. In particular, there are going to be two cases. Okay, so case number one is going to be the even mode excitation, where what's going to happen is I'm going to say V3, or V3 plus specifically, it's just going to be some value V naught, which is also going to be the value of V2 plus. So in other words, you imagine there's some signal exciting here, V naught, and another signal exciting here at the same time of V naught, represented by these little voltage sources here. Then on top of that, let's put it over here, I guess, 2. I'm going to call this the odd mode excitation, like so. We're basically going to say V3 plus is equal to V sub 0 again, V naught, but that is going to equal negative V2 plus. Okay, so we'll have the same magnitude but a different sign as we excite this network here. So for example, let's take a look at the scattering matrix here. Remember, I have V1 minus is equal to S11 V1 plus S12 V2 plus S13 V3 plus. So what I've done is I've essentially set this term to 0, and this guy here for the even case is going to be V naught, and this will also be V naught. Okay, so for case number 1, I'm going to just write this out here. I will have V sub 0 times S12 plus S13. Okay, so that is for the even case over here. And then what I'm going to do is excite it with the odd mode of excitation, and I'm going to find that V1 minus is equal to V naught, and this guy here will be negative in this case, and so I'll get negative S12 plus S13. So that is the odd case over here. So you notice what's going to kind of happen is I'm going to create a bunch of characteristic or systems of linear equations, and I'm going to analyze this circuit to figure out what these matrix parameters have to be. So let's go ahead and do that right now. Okay, let's first explore the even mode of excitation. Okay, so what that implies is my V3 plus is equal to V2 plus, which is just V sub 0. Some voltage is exciting these ports. So I have, some voltage coming in and exciting these nodes simultaneously. So what that now implies, I'm also going to say V1 plus is equal to 0. So if I plug this into my matrix equation here, two very important little equations will pop right out. So I get V1 minus is equal to V naught times S12 plus S13. And I also get V3 minus is equal to V naught times S23 plus S33. Okay, so in other words, I just plugged in 0 for this guy, and then asked myself, what are these parameters that are going to come out? So you notice also, because of the symmetry here, whatever I get for V3 minus will also apply for V2 minus, just by the symmetry of what I've done here. Okay, so these are two equations which we're going to figure out something important. And we're going to impose a few conditions to see what happens. So the key here is, because I'm exciting these two ports here symmetrically, the voltage at these two nodes is now the same, which means there cannot be any current flowing through these resistors. And by a same argument, there cannot be any current flowing here either. So what I can do is redraw this circuit like the following. I get something like this. Here's a ground. Here's my resistor to Z0, and there's just some open circuit node here, okay, because there is no current flowing through there. Then I get this quarter wavelength of transmission line. And technically, there's supposed to be this resistor here, but again, no current is flowing, so it's as if there is an open circuit here. So I'm just going to call that R. I'm going to call this Z. And I'm just going to pretend there is some voltage, V0, exciting this whole circuit here. So all I have to do is first ask myself, what is the equivalent input impedance looking down this little length of transmission line? So I'm going to call that, say, Z in, or you could call it ZEQ, something like that. Doesn't matter. Well, obviously, this parallel piece here is contributing nothing because it has infinite resistance. There is no current flowing down there. So all I am seeing is this equivalent impedance looking down here, which is a length of transmission line with some load. Okay, so I'm just going to redraw the situation, kind of the equivalent situation here, like this. Okay, so we look down here. So there's some equivalent characteristic impedance here, which I'm just calling Z. The book just calls it Z. It seems like we should probably give it something like Z sub X, because we aren't sure what it is yet, but we're just going to leave it alone and call it Z for now to stay consistent with the book. And this load out here, this ZL, has a value of 2 times Z0. And this is, my quote-unquote load impedance here, okay? Sorry, quote-unquote Z sub L, right? My load looking down this little length of transmission line. So that's what this little schematic represents. So what is the equivalent input impedance, Z sub in, looking down this thing? Well, remember the transmission line input, or the transmission line impedance equation followed the following. So we said Z in would be, for any sort of arbitrary system like this, it was Z0 times this. So you had ZL plus J Z0 times the tangent of beta L over Z0 plus J ZL times the tangent of beta L. And we specifically said this has to be a quarter wavelength here. So what that does is the tangents blow up to infinity, and what you get, this approaches Z0 squared over Z sub L. So that's the generic case. In particular, for this situation, the Z0 corresponds to this unknown Z. So what I'm actually going to get is Z squared divided by, and my quote-unquote load is this 2 Z0 here. And I am free to pick this Z. So what value should I pick for Z? Well, the obvious answer is I don't want there to be any reflections going out here. So I'm going to impose the condition V3 minus is equal to 0. I want no reflections. I want this thing to be matched. So that means this has to equal Z0. So if I solve for this mysterious transmission line impedance here, what you get is simply Z is equal to the square root of 2 times Z0. So if I choose this value for that characteristic impedance, I am guaranteed there will be no reflections here. Under the even excitation, okay, it's going to behave as if it's matched. So I've imposed the condition, this is 0 and this is 0, so what you find, a simple consequence of that is 0 is equal to V0 S23 plus S33, which now implies S23 is equal to negative S33. Okay, so this is a condition that must be satisfied. It's one equation with two unknowns. So if I can get another equation on this, I'll be able to solve for these two parameters here. And so that now leaves, what do I do with this V1 minus here? And the answer is, well, technically, the voltage here, any voltage signal that gets down here, because there's no reflections coming out this way, so whatever the voltage is at this node here is essentially V1 minus. It's just going to have to kind of keep on going down into that, that load, right? So that is V1 minus here. So I'm now just going to write this out as the usual transmission line voltage equation. So I'm going to assume this is a value of z equals 0, so that's a position. And out here is a value of negative lambda over 4. And I know that my voltage as a function of distance, position here, is V plus times e to the minus j beta z plus gamma e to the plus j beta z, right? So that is there's a wave coming in here. There's going to be a bounce back and forth here, but the transmission back here is going to destructively interfere with that mismatch here to create no reflection. So there is a wave propagating down and another one propagating back inside this little transformer here. But remember, it's matched, so as it comes back, it's going to perfectly match and get destructively interfere with that other initial reflection so that nothing net transmits that way. But there is, again, it's important to remember, there is a bounce and back and forth bounce happening here on this line. So what we know is V of 0 is equal to V1 minus, because that's just the voltage at that node here, which is going to be delivered to the load, which is, essentially at the end of the day, that's going to be the voltage that just leaves this port here, V1 minus there. Okay, and that is going to be V plus, so that's the forward propagate. I'm going to write this V plus, and then technically there's a V minus, but you'll write that as like a gamma V plus, so that's what this term represents. And it's times just 1 plus gamma, like so. Right? And then we know that V of negative lambda over 4 is equal to, that's the voltage here, which is just V naught, which is equal to V plus times. So if I put in lambda over 4 here, I get an e to the j beta times 2 pi over lambda times a lambda over 4. Okay, so that will imply an e to the minus j lambda over, or sorry, pi over 2 is what you get at the end of that, which is equal to j. Actually, it's negative j in this case, but it's negative lambda over 4, so you'll get a plus j there. And this guy here becomes a minus j times gamma. So you basically get j minus j gamma when you put in lambda over 4 here. So I'm just substituting that in for this point z. Okay, so now I have two equations here. So what we find is we get V plus, the forward propagating wave here is simply V naught divided by j minus j gamma. So then I'm going to plug that back into here. So I find V naught times 1 plus gamma divided by j times 1 minus gamma. So that is my voltage that will be leaving out. And all I need to know now is gamma. So remember, gamma is going to be ZL minus Z naught over ZL plus Z naught. So you get a 2 Z naught minus root 2 Z naught over 2 Z naught plus root 2 Z naught, which you simplify this and it becomes 2 minus root 2 over 2 plus root 2. So if you then substitute that in for your gamma here and you simplify everything out, what you finally get is V naught minus is equal to negative j V naught times the square root of 2. So that's equal to my V1 minus. That is the voltage that will leave out. So I'm exciting these two ports simultaneously, and that is the voltage that will fall out over here, because the voltage here is the same as the voltage here, and that's the voltage leaving this node here. Okay, so I've made a little bit of progress. So now I just have to plug this into up here. Okay, so let's rewrite that. So I've got V1 minus is equal to all this. So I'm going to rewrite that as V naught times S12 plus S13, which we can do a little bit of division here. And you find, let's see if I can squeeze this in, S12 plus S13 is equal to negative j times the square root of 2. Okay, so I made a little bit of progress. I figured out how all these terms have to relate to each other. I haven't figured out any of them exactly yet. So that's what's going to happen when we do the odd mode analysis. So let's go ahead and do that right now. Okay, so let's explore the odd mode of excitation. So basically what we did was we pretended to excite this network with a symmetric voltage of just the same voltage, equal, same side, exciting both of these nodes simultaneously, and we found that certain properties had to hold within this S matrix. So now what I'm going to do is pretend to excite it with a negative voltage here, so that's odd symmetry, and see what happens to this matrix under that condition. But first we're going to draw out an equivalent circuit. So remember the last time we made the argument that these two nodes had equal voltage. Since they were equal voltage, no current could flow here, and it was therefore as if this was an open circuit at this node and at that node. Now that they are opposite voltage, we have a situation where this is plus voltage, negative voltage, and everything is perfectly symmetric in between, which means right there, smack in the middle, has to be 0 volts. And by the same argument, this also must be 0 volts as well. This is a positive and negative and the same all at once. The only way for that to be true is if this is 0. So we're going to redraw the sort of equivalent circuit for this situation here. Okay, so we have this resistor to Z naught. Okay, and then there's this length of transmission line, which is a quarter wavelength, and it has root 2 Z naught. We've imposed that condition. There is a resistor here with a value of R. And there's a voltage V naught exciting this. So what we've imposed is this now has to be a short circuit rather than open circuit. So basically it's 0 volts. And same logic applied. This is now 0 volts over here. So immediately that tells us V1 minus has to be 0 for the case of odd excitation. Okay, so let's take a look now at this matrix here. So remember last time we derived these two equations here. This was subject to even excitation. When I do odd excitation, I have to add minus signs here. Okay, so in other words, remember V1 minus is equal to V2 plus times S12 plus V3 plus times S13, which is now going to be negative V naught S12 plus V naught S13, which is equal to 0. So what I get is V naught times S13 minus S12, which immediately tells me S13 is equal to S12. That has to be the case. Okay, so we have that situation up here where the sum of them has to equal this particular value here, and they are equal to each other. Therefore, S13 is equal to S12, which is equal to negative J root 2 over 2. Is that right? Am I doing that right? Yes, or you can also write this as negative J over square root of 2. That's what. Okay, so I have now just exactly solved two more of my matrix elements, and that basically just leaves a couple more issues. Okay, so I still need to choose this R value here as well. So under this particular situation, again, what I want is for there to be no reflections here. Okay, so V3 minus is equal to 0. So how do I impose that condition? Well, the answer is just look at the equivalent input impedance down this parallel combination of that length of transmission line and this resistor. So let's call that, I don't know, ZEQ, right? So we know that ZEQ is equal to, I'm going to write this as R in parallel with, let's just do this guy, Z in. So that's the equivalent input impedance looking down this length of transmission line. Well, a quarter wavelength line that is shorted at the end actually has an equivalent input impedance of infinity. So it's R in parallel with infinity, which is simply R. Okay, so to prove that, just remember, we have that equivalent input impedance followed this little expression here, and my load, my equivalent load there at the end was 0. Okay, because remember we shorted. So if my load here goes to 0, then my equivalent input impedance skyrockets to infinity. So the equivalent input impedance looking down this parallel combination is just R. So what I want now is no reflections. So that equivalent input impedance, I want that to match the characteristic impedance looking in. So that is now my ideal choice for this resistor. That will guarantee no reflections for the odd mode excitation. And we also found that I've got no reflections for the even excitation as well. So this also has some important ramifications. So we have V3 minus, so by a similar argument here, I have V2 plus times S23 plus V3 plus S33, which is equal to negative V naught, because we're under odd excitation now, S23 plus V naught S33, which is equal to V naught times S33 minus S23 equals 0. Therefore, S33 is equal to S23. So now I have two equations here that have to be satisfied simultaneously. Let's squeeze them here. So you notice S23 is equal to negative S33 and S23 is equal to positive S33. So the only way both of these expressions can be satisfied simultaneously is if they're all 0. Furthermore, by pure symmetry, anything that's true for port number 3 has to also be true for port number 2, okay? Because it's the exact same circuit, just it's the same circuit either way. So I get S22 as well has to apply here. So let's summarize all of what we've learned. My scattering matrix now basically looks like the following. I've got an S11, I've got a minus j over root 2, minus j over root 2 again, and then a negative j over root 2 here, negative j over root 2, and then 0, 0, 0, 0, like that. So the only term I am missing is S11. So let's do one last little bit of analysis to see how that works. Okay, so all I'm going to do now is redraw my circuit here like the following. So here is Z naught, and I'm going to imagine exciting this with some V1 plus. Okay, so this is now going to have my little branch here. Then I'm going to branch out down here. So this is going to be root 2 Z naught, root 2 Z naught. This will now continue on. Then this will continue on. So here is a Z naught, here is a Z naught, and there is a resistor branching from here to here. And this has a value of 2 times Z naught. Whew. Okay, so the question now is simply, what is the equivalent input impedance looking down this parallel combination? Well, these are both symmetric, right? So whatever the equivalent impedance is looking down here, it is the same looking up here. So I'm just going to call that Zn is just going to be Zx, whatever that is. So I'll just draw that, say Z sub x in parallel with Zx, which is actually just going to be, since they're the same, I'll get a Zx over 2. Okay, so this little bridge here makes things a little bit complicated until you realize there's symmetry here. So if I have a voltage from here to here, remember, it's going to excite a voltage that goes down here and another voltage down to here, and these voltages are going to be exactly the same, which means no current can flow through that resistor if I'm exciting with a voltage here. So what that means is this resistor here doesn't contribute anything. So the equivalent impedance looking down here is just going to be, again, another transmission line input impedance equation. So my Zx is going to be, so remember, it's the characteristic impedance squared divided by the load, right? So I'm going to get root 2 Z naught squared divided by Z naught there. So in other words, the more generic expression, it's Z naught squared over ZL. So that's for a quarter wavelength. So in this case, the Z naught is this transformer length, root 2 times z naught, and the load, quote unquote, is a z naught down here. So what I'll get is simply 2 z naught squared over z naught, which is equal to 2 times z naught. So the equivalent input impedance, looking down to that parallel combination, is this over 2. So what we'll find is z in is equal to z naught. And it's matched. Therefore, V1 minus is equal to 0. All right, so what you basically have is V1 minus is equal to V1 plus S11 plus, I'm not exciting these, so there's nothing. And you find S11 is equal to 0. Okay, so in summary, that tells us the net scattering matrix for a Wilkinson power divider will look like this: 0, 1, 1, 1, 1, 0, 0, 0, 0 times negative j over square root of 2. Okay, so that is the scattering matrix for a Wilkinson power divider. And so what's great is it's a great tool for just splitting energy down into 2 equal parts. So it perfectly divides any incident power by 2. So half my power goes down this line, half my power goes down that line. They both have the exact same phase, so they're in phase with each other, which is often very important if you want to preserve kind of a phase relationship between your signals. You notice it just has a slight phase delay here of like 90 degrees for the signal that goes down. And that 1 over square root of 2 is what you get when you're reducing the power by a factor of 2, right? So if I square that, that tells me power. So I have half the power going down each line. Okay, so there you go. That's the Wilkinson power divider in a nutshell.